Okay, so we start the morning session with Akim Ken from Waterloo. You see the text here. Title slow, please.
Thank you very much. Good morning, everybody. Today I will talk about the solution to a problem that's very dear to my heart. It took me more than 10 years to figure this out. And in hindsight, I think, what took me so long? And in hindsight, the solution is not that complicated after all. But then the problem is more than 100 years old, so maybe the 10 years is okay. So the problem I want to talk about is spectral geometry. And many of you may know what spectral geometry is, but let me just quickly review. So Hermann Weyl, more than 100 years ago, asked, if you have an object and you make it ring, for example, by tapping it with a spoon, then you will hear a sound that it makes, and you can record the vibrational spectrum, and clearly the spectrum depends on the shape of the object. The bigger it is, the more deep the sound will be, and small things will vibrate with a higher pitch. But he was wondering, how much can we learn about the shape from the sound alone? Now, why would that be of interest? Sure, it might be of interest for pure mathematicians, but I think also for physics. And the reason is that if we were to succeed with spectral geometry, if we could hear the shape of things, then we would have a mathematical bridge between differential geometry that describes the shape of things, and which is the language of general relativity, and functional analysis, which describes the spectra of things, which is the mathematics of quantum theory. So it would be amazing if we could build this bridge, if we could describe geometry in functional analytic terms. If we could describe the shape of things in terms of their sound. But does it work? And many of you may know that there are counterexamples. There are shapes that are different, but they sound the same. They have the same vibrational spectrum. At this point, one may give up and say, well, it doesn't work. But after all, eventually we need, one way or another, we do need a bridge between differential geometry and functional analysis. Something of the kind of spectral geometry is needed because quantum gravity combines gravity and quantum theory, and therefore intrinsically must combine differential geometry and functional analysis in a very deep way. So I thought, let's not give up so quickly. Let's see, maybe it is possible to hear the shape of things. And of course, it's not about metal objects that might vibrate. No, the curved thing that we care about is space-time. And the vibrational spectrum of a metal thing, well, you know, this could be the vibrations or the fluctuations of quantum fields that live on that space-time. But let me get back to the physics of curved space-time and quantum fields that live on that space-time towards the end of the talk. To keep things very intuitive, I'd like to stick with the picture of a vibrating object that we can visualize. Something like an irregular shape like that of a potato. And imagine that we have a thin metal sheet in the shape of the surface of a potato, so some irregular body. And we want to hear the shape of this thing. So how might we hear that, given the fact that we know that just tapping the potato, the metal potato, just tapping it and recording the frequency spectrum is not enough. Generically, it's not. There's a class of cases where you can, but generically, it's not enough, especially not in higher dimensions, like 4. What else could we possibly hear? Isn't that all we can hear, that we tap it and then it vibrates and we Fourier transform what we hear and we get the spikes and this is the spectrum? Actually, there's one more thing that we can hear. And that will save the day, and we can do spectral geometry, we can hear the shape. So what else can we hear? Imagine you take again this metal surface, the shape of a potato, and you tap it. That's the first part of the experiment. You tap it, you record the sound, Fourier transform it, record the resonance frequency, the resonant frequencies. That's the part one. Part two is the new one, which is that we take the same potato and we hit it really hard, so that the vibrations are of such large amplitude that the oscillations that are triggered are no longer harmonic, that they get into the non-harmonic regime. What does that mean? What happens there? And you might imagine in the cinema of the mind what might happen. So you tap the potato, the metal potato, lightly, and you hear some harmonic sound. Sounds perhaps good, depends on the shape of the potato. But if you hit it hard enough, you will hear a weird kind of sound. It will sound more metallic, it will sound weird. What's going on there? What's going on is that nonlinearity means interaction. I don't know if everybody's completely clear about this, but nonlinearity is interaction. If you have linear equations of motion, then the sum of two solutions is a solution. Example, two beams of light. Each one is a solution to the linear Maxwell equation. So the sum of them is also, which means the two beams of light pass through each other without affecting each other. There's no interaction. But make it a nonlinear theory, just like water waves. In this case, water waves easily get into the nonlinear regime. So now the sum of two solutions is no longer a solution. Water waves can go like this. I mean, that's the strongest case, but even if they don't splash, water waves interact with each other. Whenever you have a nonlinear differential equation, the sum of two solutions is generally not a solution, which means exactly that two waves will interact with each other. They will not just superimpose. So on the surface of our metal potato, if we hit it so strongly that we get into the nonlinear regime, then those standing waves, those so-called modes, start interacting with each other. And that
change the shape of the potato.
No, I don't want to change the shape. So when you make it oscillate so strongly, then the modes will interact with each other. And what that means is that the sound changes. You get a phenomenon whereby sound makes sound. Namely, you excite some of the modes, and then they will excite other modes. The harmonic oscillators will interact with each other. By the way, that's exactly what happens in quantum field theory too. The linear equations of motion describe free particles that don't see each other. Put a nonlinearity in the equations of motion, and they start scattering of each other. Nonlinearity is interaction. So, this is now the part two of the experiment. Part one of the experiment is the usual spectral geometry. You tap your potato, you record the resonance spectrum just by listening to it, Fourier transforming. Record the resonance frequencies. Part two is you pick two of the resonance frequencies and you drive the potato at those two resonance frequencies. Initially, it will just resonate at those two frequencies. But if you increase the amplitude, you get into the nonlinear regime, and those two standing waves will have amplitudes large enough so that through the self-interaction, other modes will also be excited. So even though you only excite frequency F1 and F2, you might also get some other frequencies F3 and F4. That's what you would get if you have a phi to the 4 nonlinearity, for example. And this exactly happens in solids, where you have the phonon-phonon interaction. It's the phi to the 4 theory, and you can have that. It has impact on heat conduction, electrical conduction, and so on. Okay, but we're interested in the acoustic properties here. So part two of the experiment of listening to the vibrations of an object is that we pick two resonant frequencies that we already established, excite them both very strongly, and then we measure what other frequencies we might hear. And as we get into the nonlinear regime, two other frequencies might appear. we record to what extent they appear. And we do that for all pairs of resonance frequencies. Coming back to quantum field theory, remember the linear regime, linear equations of motion mean particles don't see each other. The nonlinear regime is where they have interactions with each other, and we record all that. That's what accelerators do. And what you get is the S matrix. But coming back to the acoustics, we do that. Instead of having two particles created and crash into each other at the LHC, no, we just have our little metal potato. We excite two resonance frequencies, two modes, and then record not what particles scatter out like in the LHC. No, we just record what other frequencies will be excited and to what extent. So the thing with the potato is just a purely classical thing. And we record that for all the pairs of resonance frequencies. That's purely acoustic information. It does not depend on coordinate systems. You know, there's no diffeomorphism group to mod out. It's just purely acoustic information. And my claim is that these two parts of the experiment, first tapping lightly and recording the resonance frequencies, and then exciting two resonance frequencies strongly and recording what other resonance frequencies will be triggered by that, that's the second part of the experiment. The data that we obtain together tell us the shape of the object. And we can explicitly calculate the shape from that purely acoustic information. And I will get at the end to what that means for the physics of it, for particles that live on a curved space-time, and how, by doing particle experiments that are of the acoustic kind, so to speak, just scatterings, the S matrix, how we can actually, from that, infer the curvature. At the end of the day, what I'm claiming is that we have a method by which we can take a mobile LHC, if such a thing ever gets developed, take it to some place in the universe, let it perform its scattering experiments, measure the S matrix, and from the S matrix we can determine the curvature of space-time where the thing is. Okay, I just told you everything on the first few slides, and I thought it would be better if I just not distract you with the text there as well. But if you want the slides have what I just said already. Okay, thank you. All right. Okay, so the key insight was that in the nonlinear regime, sound makes sound. You excite some modes, and through the nonlinear interaction between the modes, between the harmonic oscillators of the different standing waves, other resonance frequencies will be excited. So then, how do we calculate the metric? How can we make spectral geometry work? We perform two experiments, as I said. We tap lightly. Is there a laser pointer? Ah, yes. Oh, it's a little feeble there. All right. Okay, so experiment A, as usual, you tap lightly, you record the frequency spectrum. Experiment B is you excite with pairs of resonance frequencies, and then you pick up what other frequencies are being excited, and you get a matrix of acoustic data in this way. A matrix where you excited on purpose the N's and the M's resonance frequencies strongly, and then you check how much, therefore, will be the U's and the W's resonance frequency be excited in the process. So what is that matrix V? Well, it's actually just the interaction Hamiltonian. So for example, for phonon-phonon interaction, it would be lambda phi to the 4. And when we measure it purely acoustically, then what we do is the numbers that you get when you excite with two resonance frequencies and you pick out how much, you measure how much this and that resonance frequency are excited, that's the number you put into this matrix. So two resonance frequencies in, two resonance frequencies out. So these are the eigenmodes. You don't need to know how they look. You just measure that overlap. That's directly the measurement data, these numbers. I mean, two prefactors and so on. So this is the self-interaction Hamiltonian, interaction Hamiltonian. This is the hearable outcome of experiment B, of the nonlinear part. Then what I'm claiming is that from these acoustic data of experiment A and experiment B, we can explicitly, constructively calculate the metric. And not just for two-dimensional Riemannian compact manifolds. No, also for the Lorentzian signature case and any number of dimensions. Okay, so for this, we need to achieve this goal. We need to obtain the metric from those acoustic data. And here's the first step. There are 5 steps. And that was quite an adventure to figure out what they would be. 10 years. Okay, so step 1 is this. We say, we want to obtain the metric. The metric describes infinitesimal distances, right? So we can certainly obtain the metric from the finite geodesic distances. Right? The metric is just the infinitesimal geodesic distances. And so if we have the geodesic distance function, sigma of x and x prime, it's also called the Singe function or the world function, if we have that geodesic distance, in fact, sigma is defined to be 1/2 of the geodesic distance between x and x prime. If we had this, then we could obtain the metric. Namely, and this is a long known formula, you can take, if you have the geodesic distance, then you can differentiate it with respect to both of its arguments, take the coincidence limit, and you get the metric. It just says the metric is the infinitesimal limit of the geodesic distance. Fine, but we don't have the geodesic distance. We don't hear the geodesic distance, right? So we'll have to somehow get the geodesic distance now in order to get the metric. Well, we can do that because we can obtain the geodesic distance function from the wave propagator. So we have our metal potato, and there's a Green's function on it, right? There's a Klein-Gordon equation living on this metal potato with a 5⁴ self-interaction. And if you solve for the Klein-Gordon equation on that metal potato, you get a Green's function. And that Green's function obeys the Hadamard condition. It always does. And I'm talking here Riemannian manifolds, Lorentzian manifolds, always true. And what that means is that this Green's function has this divergence in the coincidence limit. So as x goes to y, the Green's function of our waves that live on this potato, the Green's function starts with a 1/sigma divergence plus other terms that are subdominant. This is the dominant term. What this means is that if we knew the Green's function, if by whatever means we can figure out what the Green's function is, at least in the coincidence limit, then we get from that what the geodesic distance is in the coincidence limit. And from that, as we saw previously, we can get the metric, right? Okay, so we can get the metric if we get the geodesic distance function. But the geodesic distance function actually can be obtained from the Green's function because the geodesic distance function is the leading divergence of the Green's function. So therefore, we can just pick out that term, and you can convince yourself with a little calculation that if you take the Green's function, assuming you have it, you take the Green's function, take 1/it, differentiate with respect to both arguments, take the coincidence limit, then up to prefactors of powers of pi and so on, and these, I calculated those, give you then the metric. So this is in itself already an interesting result. It means that, you know, a Riemannian or Lorentzian manifold is usually described as a differentiable manifold plus a metric tensor. But you know, you can also describe it equivalently as a differentiable manifold with an affine connection on it. You can also equivalently describe it as a differentiable manifold with a geodesic distance function sigma on it, because the sigma obviously gives you the metric. But you can also describe your Riemannian or Lorentzian manifolds as a differentiable manifold plus a propagator on. because the propagator gives you the asymptotics of the in the coincidence limit, it gives you the geodesic distance, and therefore it gives you the metric. So if on a differentiable manifold, on a space-time, you know only the propagator, let's say you know only the Feynman propagator, but you don't know the metric, you don't know the affine connection, you just have an explicit form for the Feynman propagator, good enough. It tells you what the metric is. By the way, that power here is dimension dependent, and the 1 over sigma is characteristic for 4D. In other dimensions, it's a different power. All right, so far we know we can get the shape of the manifold, we can get the shape of our momental potato, we can get the metric if we can figure out the Green's function. But can we hear the Green's function? How would we hear the Green's function? It's a function of x and x prime. So the next step, step 3, is to overcome this. You see, the problem is we cannot directly hear the Green's function. Except we can. We just can't hear it in the position basis. We can hear the Green's function in its eigenbasis, because we can hear the resonance frequencies. See, we can take the Green's function, and instead of writing it as a function of x and x prime, we can write the Green's function in the eigenbasis of the Laplacian. So we diagonalize the Green's function. That's that. And then we do a change of bases in the space of functions or fields that live on our metal potato, or space-time as the case may be. So we take the change of basis u that takes you from a position basis to the eigenbasis of the Laplacian, or the eigenbasis of whatever wave operator you have, a Dirac operator, or the wave operator of electromagnetism, and so on. So up to a change of basis from the eigenbasis of the wave operator to the position basis, up to this unitary change of basis in the space of fields, we can actually hear the Green's function, because the Green's function in the eigenbasis of the Laplacian is diagonal, and the diagonal entries are the resonance frequencies. And this we can hear. So you might say, oh, okay, so the old-fashioned spectral geometry works. You're telling me that we can hear the spectrum, and the spectrum is the Green's function in its eigenbasis, so therefore we have the Green's function, therefore we get the world function, therefore we get the metric. Not so fast. Here we see what's missing. What's missing is we need this unitary here, right? We need to have that unitary, because yes, we can hear that. We can hear the resonance frequencies, the eigen values of the Laplace operator, which of course implies the eigenvalues of its inverse, the Green's function, right? So that part we can hear. The part here, no, it doesn't, yeah. That thing we can hear, the resonance frequencies, but how can we hear this, the change of bases? We still need this. The only thing we can really hear is those numbers. That's why we need 2 more steps here. We need to figure out now how to also get the unitary change of bases from the eigenbasis of the Laplacian to the eigenbasis, to a position basis. How can we do that? How to obtain this unitary change of bases? Well, nature is local. Interaction Hamiltonians are local. And what that means is that in a position basis, and there are many, because every coordinate system provides a position basis for your space of functions, in a position basis, and only in a position basis, is our interaction Hamiltonian diagonal. That is to say, the interaction Hamiltonian, depending on these 4 positional arguments, is some function times these Dirac deltas, which ensure that the interaction Hamiltonian is non-zero only when all arguments are the same. When x is equal to x prime is equal to x double prime is equal to x triple prime. This means that we can identify positional bases in the Hilbert space of square integrable functions on the manifold, like on the potato, we can identify positional bases not by diagonalizing position operators, because we don't have them here. No, by diagonalizing the interaction Hamiltonian, because it is local. So any basis in which the interaction Hamiltonian is diagonal, meaning this, any such basis is a positional basis. So all we need to do is we take the matrix elements of the interaction Hamiltonian, which we measured. Remember, we hear them. Thank you. We can actually hear the matrix elements of the interaction Hamiltonian in the eigenbasis of the Laplacian. How do we do that? Well, we excite our potato with two frequencies very strongly to get into the nonlinear regime, and two other frequencies are also excited. And how much? That's the entry of the interaction Hamiltonian in the eigenbasis of the Laplacian. And then we get this matrix. It's just actually a 4 tensor. It's not a matrix with 2 indices, with 4 indices, because it's a phi to the 4 interaction. It's a 4 tensor that's totally symmetric and covariant. These things can be diagonalized. It's not like diagonalizing a 2 tensor like an operator, though. And the diagonalization is not unique, and it shouldn't be, because every diagonalization is another coordinate system. But there are methods to diagonalize 4 tensors, and we can just diagonalize the V, and the first diagonalization that we find, we pick. We could also pick any other one, doesn't matter. And what we obtain, therefore, is a diagonalization of the interaction Hamiltonian. That means we can express a positional basis of the x's in terms of the eigenbasis of the Laplacian or of the Green's function, which means we obtain a solution for this unitary x and Vn. Diagonalization means change of basis from the eigenbasis of the Laplacian to a positional basis. So V is a diagonalizable 4 tensor, so we obtain diagonalizing unitaries, which when applied to our interaction Hamiltonian diagonalizes it. In other words, we get a position representation. So we obtain explicitly from that diagonalization process, we explicitly obtain those unitaries. Each choice of diagonalizing unitary gives us another coordinate system. So that means we can hear all we need. We can hear the spectrum, but we can also hear the change of basis. And the conclusion is that from experiment A, tapping the metal potato lightly and therefore recording the resonance frequencies, we obtain the omega n's, which are the eigenvalues of the Green's function in its eigenbasis. And we obtain from the second experiment, experiment B, where we drive the metal potato with 2 frequencies and then listen into what other frequencies it excites, and then diagonalizing that interaction Hamiltonian, we obtain the diagonalizing U. And so therefore, we can take the Green's function that we initially only know in its eigenbasis, because we only know its resonance frequencies. Well, once we have the diagonalizing unitary, we can take the Green's function and take it from its eigenbasis to a positional basis. We have then the Green's function as a function of x and x prime. And from that, since it obeys the Hadamard condition, we get the geodesic distance. And from that, we get the infinitesimal geodesic distance, and that's the metric. It's a bit of a winded road, but it gets us there. So the final result then is that we can always determine the shape from the sound if we have a self-interaction on the manifold in question, such as the phi to the 4. There's nothing magical about the number 4. It could also be phi to the 3rd, or it could be 2 fields that interact with each other. Any interaction Hamiltonian is only diagonal in a positional basis, and that provides us with the ability to calculate these unitary changes of basis. So once we have the unitaries, we get the Green's function in the position basis. From that, we get the geodesic distance function, and from that, we get the metric. So we can always determine the shape from the sound. So what does this mean for quantum field theory on curved space-time? Well, the metal potato, after quantization, what does the metal potato correspond to? Well, the curved surface of the metal potato is a compact Riemannian manifold, but we can just as well do this for curved space-time. And then what does experiment A correspond to? Where we just tap our metal potato lightly to get, the first order excitations that are obeying linear field equations and therefore no interaction. Well, that's, in particle physics, that's the excitation of free particles, making sure that they don't interact with each other so that everything stays in the linear regime. We are measuring the particle spectrum. So instead of listening to the frequencies of the resonance frequencies of the metal object, we are measuring here the eigenvalues of the D'Alembert or Dirac operator and so on. Which gives us in general a pretty trivial diagonalization, a diagonal matrix, because on a non-compact, Lorentzian manifold, the spectrum of the D'Alembert will be continuous. It has extremely little information in it. But we don't care because we have a trick up our sleeves, right? Which is that we perform experiment B as well. And experiment B means, we drive with two resonance frequencies the metal potato. But in particle physics, this means we crash particles into each other and we measure the S matrix. The V matrix is the S matrix. So we measure that. And that tells us how the S matrix gives us, on curved space-time, it gives us the unitary change of basis from the eigenbasis of the wave operator, where we measure the S matrix, to a positional basis. And that means that we can write down the Green's function no longer only in its eigenbasis, where it's just some trivial diagonal matrix. No, we can now transform that into a positional basis. We get like the Feynman propagator or the Whiteman function. And then from that, we can, in the coincidence limit, get the geodesic distance. This works because the Hadamard condition is true also for Lorentzian manifolds. So we get the geodesic distance, and from that the infinitesimal geodesic distance, which is the metric. And so this means the following. What are the takeaways? This is the last slide. I promise, the last slide. So what are the takeaways here? There are physics takeaways and there are math takeaways. The physics takeaways are this. The S matrix completely encodes curvature. We don't usually do S matrix theory on curved space-time, but if we did, what we would find is that the S matrix knows all about the curvature. And why does it? The S matrix tells you, if I take a particle with this momentum, particle that momentum, then I create those particles with those momenta. On a curved space-time, momentum is not conserved, neither is energy, right? You have non-conservation. If there's curvature, the S matrix knows about it because it knows that there is non-conservation of these laws. This is a vast generalization of Noether's theorem. Noether's theorem tells you if there is symmetry, then there are conserved quantities like momentum and energy. But this tells us that if momentum and energy are not conserved, and we measure exactly how it is not conserved by measuring the S matrix, then we will find that the underlying space-time is not symmetric, and instead we find out exactly what the metric is. See, Noether just tells you about the special case. Symmetry, or good, you get conservation. This tells you any kind of non-conservation, you can calculate exactly how it's non-symmetric. You can calculate exactly what is the curvature of the space-time. So in practice, if you had a pocket LHC, the size of a smartphone, which can run, scattering experiments, you could go around and measure the curvature of space-time. Okay, so what is the mathematical takeaway here? The mathematical takeaway is that geometry can be expressed purely in terms of frequency data. Differential geometry can be, for Riemannian Lorentzian manifold, can be expressed completely in terms of frequency data, but it's not just the spectrum of the Laplacian or D'Alembertian. No, you need a nonlinear theory. You need self-interactions, and then listening to how certain resonance frequencies, or how any pair of resonance frequencies creates other resonance frequencies, how particles create other particles. That's what you need as well. It's purely acoustic data. There's no coordinate system needed for this. But if you have that purely acoustic data, then you can describe your differential manifold, and therefore you have a kind of mathematical bridge between, yes, this is the last sentence. Right, so you have this mathematical bridge between GR and quantum theory, and we applied this general idea to quantum gravity. That's a paper with Barbara, who is sitting over there, and with Marcus Weitz, if you're interested in this. Thank you very much.